started. Hello, everybody. Welcome to the CSS seminar series. For this week, we have Dr. Dashun Wang, who is the Kellogg Chair of Technology and Professor at the Kellogg School of Management at Northwestern University. He has a strong focus on complex systems and complexity science, and uses a lot of the tools in that field for his interdisciplinary research that spans a broad range of fields, including social networks and human mobility patterns at large scales. Really interesting studies about how people move and how they're predictable when there's like a large shock or unpredicted or unforeseen events. So these are, I guess, more the early works of Dr. Wang. More recently, he's been working and pioneering the new field of the science of science. He leverages large-scale bibliometric and other metadata sources to understand how papers make influence and impact in terms of their creativity, disruptiveness, and herding effects, as well as aspects of the scientists' successes, setbacks, and collaboration. So both at the paper level as well as the individual scientists, he covers a really broad range of topics and issues. And more recently, he's been looking into benefits and challenges of AI in scientific research. And he's also an important key institution builder of the new science of science, popularizing this nascent field, and also streamlining research by building really extensive data lakes so that researchers can take advantage and really bootstrap their research in this field. So without further ado, please welcome Dr. Dashun Wang.
Hi, everyone. Thank you, Patrick, and thanks for having me here. It's a real pleasure to be here. I'm very excited to be here. It's actually my first time, I realized, at a CMU. And it's like most people actually, it's hard to believe it. So it's very excited. Very exciting. And so I'm the recovering physicist at Kellogg, and where I had the Center for Science of Science and Innovation, which is the first center worldwide dedicated to this area of science. So I thought what I'm going to do today is just give you a flavor of, I select a couple of projects in the field and just give you a flavor of kind of work that we do in this kind of area. I should also preface, as we're just talking about sending students each other's way. So we are in a phase of very significant growth. So we're hiring very aggressively right now, especially in my team, with the launch of a couple of new initiatives. So we're hiring really at all levels, right? So this includes pre-doc, graduate students, PhD students, postdoc, especially, and research scientist level, as well as at the tenure track level or tenured level. So really all levels. So if you're interested, let me know. And we're really looking forward to expanding the team. And the team is extremely interdisciplinary. Just give you a sense. In the center right now, we have, recovering physicists like me or applied mathematicians, as well as computer scientists who pushes AI stuff. We have political scientists who think about the intersection of science and politics, or sociologists, and management scholars. And in terms of the PhD students, if you're interested in the program, for my lab, I'm recruiting through now 3 different programs, including McCormick School of Engineering, Kellogg School of Management, as well as physics department. So pick your poison, and we are there for you. All right, so let me get started on the talk. All right, science of science. So let me give you a 1-minute intro on what is science of science, okay? So if you think about timeline, I think 2018 is an exciting year for the field, where we published the first review paper for the field. It's called Science of Science in Science. Later that year, Science also put out a special issue, putting us on the cover, arguing to vote more scientific science. 2021, we're also excited about the first book for the field called The Science of Science, right? So in many ways, this idea of turning scientific methods and curiosities on science itself, this is not a new idea, right? This is an idea that dates back to at least mid-past century. There are a large number of founding giants of the field. Think about Robert K. Merton, the great sociologist of science, thinking about the idea of Matthew effect, singletons, multiples. Priscilla Price, another physicist turned historian of science, thinking about the idea of invisible college, power laws, cumulative advantage. Harald Zuckerman at our Columbia Sociology School of Sociology, we use an ethnography approach to understand the careers of scientific elites, right? Or Eugene Garfield, the father of the science citation index, they invented this thing called citations that many of us continue to love and hate. Or Bob Solow, the late Nobel Prize winning economist, that pinpoint innovation as a key driver for growth and technological progress. And of course, there's Thomas Kuhn, one of the greatest thinkers of 20th century, thinking about the idea of paradigm shifts. So I think in many ways, this new surge of interest of understanding science is to stand on the shoulders of these giants, but then take two things that they did not have the luxury to have in their time. First is the increasing availability of massive data sets that captures the entirety of the scientific enterprise and tracing its inner workings at a fundamentally new scale and detail. I'll give you a sense of how much new data is becoming available. If I look at my own lab's work, over the past 8 years, it's very easy to say every year our research agenda has been shifted because the new data became available that we didn't even know the year before. You know, it's happening to us now. It happened last year, it happened the year before that. We had a science paper published in 2021. The data on that paper we didn't even know was possible before the summer of 2020. So that's kind of how rapidly new things are coming at us. At the same time, I think that's one factor. The second factor is the parallel developments in fields like AI, network science, complexity science, that really offer us a whole range of new toolkits that actually make sense of this data with a fundamental new level of accuracy and robustness. In other words, if we had this data 20 years ago, we wouldn't get much knowledge out of it because we wouldn't know what to do with it. But now it's really the convergence of data and toolkits that allow us to tell a very complex but insightful story about how innovative careers unfold, how collaboration spark discoveries, and how progress may emerge through multiple interconnected factors. And oftentimes we also find that these kind of insights, not only they're of great interest to scientists ourselves. I always say, as a scientist, what do we love the most? Ourselves. And there's also of great interest to the scientific community, but also we see that these kind of insights often they have implications for science policy, entrepreneurship, sustainable business innovations, etc. Right? So technological progress more broadly. So that's kind of the genesis of the field. So what I want to do today, as mentioned, sort of in the lab, there's a different subdivisions, what I call different departments. You know, there's an AI department to try to understand AI implications for science, and we divide a whole range of large language models, 3 different kind of fine-tuning. So there's the CS department, there's political science department to try to understand political science of science, and there's sociology department, there's the physics department is about a mathematical modeling of everything. I thought what I'm going to do today is to pick up one line of this kind of research where I want to talk about a journey of research. We're trying to understand how patterns unfold through a successful career. And so around the question of where do breakthroughs come from, all right? I want to use this line of research and illustrate a range of projects. So this includes old projects as well as recent projects through this line of journey to help you illustrate sort of the type of work that we do on this. So give you a flavor of for the type of work we do. And now I'm going to touch briefly in the end to talk about some new project we're starting, which is to say the basic idea is given what we have learned on the science of science over the past 10 years, what we want to do in the next 10 years is to think about how do we use AI and all these insights to accelerate scientific and technological progress. So this is something we're just embarking now, and we really need a lot of help, and especially from people who are technically proficient. And I hope what I hope to illustrate to you is in my view, with the science of science, what lies ahead of us appears to be a unique opportunity to greatly advance the R&D success. So hopefully this will come away as a message. All right, so let's get started. Innovative people, where do breakthroughs come from? So this is a question. I call this project the Hope Project. This is a project that started about 10 years ago. The idea here is to say, I look at so back then I was much younger, no gray hair and stuff like that. And so, but I look at all the people that I admire, I wonder, are there patterns in terms of like, when do they do their best work? And what happens after you produce a major breakthrough? Will you do a better work after a major breakthrough, or are we dead, scientifically speaking? So this is why I call this a hope project. Is there hope left in the career? And so this is a question that obviously has fascinated economists, psychologists, and a range of scholars. Dates back to at least 2 centuries ago. All right, so the people always wanted to ask this question. And this is a question that actually used to have a very simple answer. When do you do your best work? You do your best work when you are young. All right, so the exemplifier of this is basically these 2 people. Einstein famously said, a person who hasn't made his great contribution to science before the age of 30 will never do so. Usually in the room is pretty depressive after seeing this. Or this guy, right, who just went through one of the most expensive midlife crises, who used to say, young people are just smarter, right? So if you look at the data actually seems to suggest this view and supports this view actually in a very robust way, all right? If you look at the data, what do you typically see? When do you do your best work? Is this singular peak that's somewhere around your mid-career, 30 to 40 years old. No matter how you measure it, over and over, this is extremely robust, all right? So this is the data I took from Ben Jones, my colleague, one of his papers, where he looked at all the Nobel Prize winners of the 20th century, and then similar period, the greatest inventors, and asked, what age did they do their best work, all right? So what you see is this peak, right? Somewhere around 30 to 40 years old. And this is very simple, intuitive to understand. The basic way to say this is, there's no 4-year-old has ever won a Nobel Prize because when you start, you have to learn. Right? As you're learning, then the innovation starts to peak. Right? And then that peaks sharply rises up to a certain peak and then followed by a gradual, if a very brutal decline. So it sounds like then this is sort of many people then interpret this as a very hopeless message where as you get older, it seems like the chance for a breakthrough become very bleak. All right. So we came into this. We had 2 realizations, which about the data, right? First realization is, well, these are about Nobel Prize winners. I kind of like, I wonder about me. This is kind of this is even relevant for people like me. So I want to sort of expand the data collection in that sense, being more comprehensive, more inclusive, right? So second realization, which I think is more important point, a subtle, but we'll get to there, is that if I want to know where do you do your best work, my data shouldn't include just your best work. I should include all the work you do and look at where that best work is situated. Right? Does that make sense? So this is sort of illustration. This paper was just 10 years old, but in the past, 10 years ago, there is no data. So all you have to do, you have to hand collect the data. So if you hand collect data, of course, you go through Einstein first. Of course, you just get 1 data point for each person. But if you look at Google Scholar, for example, then all the papers are there and you can look through them in however way you like, right? So that's kind of like where we want to look at. So I thought then the easiest way to say is, let's get all the papers and look at where the best paper occur, all right? So here's some new data. This is a very complex figure. Let's go through them one after another, all right? So here panel is about scientists. So here we're looking at 20,000 scientists. So this is about 100 times more than the state of art at the time. All right, so 20,000, and this sort of spans all disciplines. And then we look at, for all the scientists, we have all their papers, and we look at within the sequence of work they produce, where does the best work situate? All right, so what you see here is a cumulative distribution in the sequence that follows a straight line. So what it means is that in the probability density function, this is completely flat, all right? So what this is telling us is that in terms of within the body of work you produce, your best work actually occurs with equal probability. It could be your very first work, very last work, or somewhere in the middle, all right? So if you look at this results, then you realize, actually, if I reproduce what everybody else measured before, I will still get the same conclusion, which is you still do your best work when you're 30 to 40 years old. But that's not because age and creativity are intertwined. It's just because you produce a lot more during that period. All right, do you get this, right? So if you look at thinking about your career as a lottery ticket, every time you publish a paper is a lottery and a random number. Then if a certain period in your career, you go to that lottery station a lot more often, then you will see that, you tend to observe a peak around that period, right? So in some sense, what this data telling us is that what we observed in the past were still true, but it gave a new meaning to how that data ought to be interpreted, right? Because in this plot, in the interpretation here, is that some people then actually took it further, call me a Mr. Hopeful for this plot, which is called now in the literature called a random impact rule, which is to say, actually there's a lot of hope. As you get older, conditional on producing a paper, the hit rate remains remarkably stable throughout your career. So that means actually if you keep producing, maybe a breakthrough is yet to come. So that's kind of interesting, but let me then go further from here and then think about, okay, so what about other domains, right? So now if I expand this to other domains, what will happen? So then we went ahead and collect data on artists and all the artworks they produce, and this spans about a span of 500 years now, right? So scientist data is more about past 60 years. Artist data is past 500 years, and then we look at all the artwork you produce, where is the most best-selling artwork that's situated. And you see, actually, obviously it's a different setting with different setup, and it actually seems quite consistent with what we observe with scientists. And then we say, okay, well, what happens if we go to another domain? And so we then went ahead and look at all the movie directors over the past 100 years and look at where do the best movie that's situated. And this is the plot for directors. And you're seeing, again, very similar pattern, right? So that's kind of interesting because this is telling us, okay, well, there's actually also this random impact rule. Not only is kind of interesting, but also is of great relevance across wide-ranging domains. But let's then take it one step further from there, which is, so the thing with you having systematic data is you can ask questions of, well, what about a second biggest hit? All right, so just for every individual, what if I just look at your second best work instead of the best work? All right, what happens there? Or we can say, I want to look at precisely the third biggest hit instead of anything else. And look at that for everybody, what happens there. So this is where we go back to this plot. They actually have 3 colored dots, right? So, and it's a little harder to see because they largely overlap with each other. So then you will have new questions because now you're saying, okay, well, you told me it's a random impact, but now second biggest hit is also random. The third biggest hit is also random. So what does that mean? Because that really then seems to me, then immediately you have a model for a researcher, which is completely just a lottery ticket. Everything is random, right? But that also doesn't make sense because we know if we produce a big hit, kind of like, that gives me more funding, more students want to work with me, and kind of I figured out some trick to produce that hit. And all of this, we know massive effect, we know rich get richer. So all of this should actually help me produce another hit. But if everything occurs random by itself, then that actually means our conditional on producing a big hit, your next paper is more likely to be mediocre than spectacular because regression toward the mean, right? So what happens there? So it took us a long time, but finally, when we look at this measure, we start to figure out where it happens. So the puzzle crack open when we look at a relative timing between your biggest hit and second biggest hit. That is, I look at, if I know where your biggest hit is, I know very well where your second biggest hit is. It's just around the corner of the biggest hit. And if you look at similarly, the first versus third, second versus third, you're seeing similar pattern or a clear diagonal pattern, right? So what this is telling us is that, well, the timing of each hit within a career appears random by itself. Their relative timing, however, follows a very predictable pattern. What we realized then that allow us to develop a mathematical model for the career patterns, which is the most consistent explanation we find is this idea of health streaks, right? The idea of health streak is think about your career as you're starting your career at a certain level, you produce one paper after another, drawing from a fixed distribution, right? At some point in your career and a random point in your career, you all of a sudden elevated to another level. It's like you're not yourself anymore. It went to like a super saiyan, if you know what I'm talking about. And then you stay on that level for 4 to 5 year period, and then you fall back to where you were before. All right. So this is a mathematically trackable model. Once we apply this model, we realize actually quickly can explain all the patterns that we observed so far in terms of real careers. But what's really interesting about this model is then we can fit it to real careers and learn a little bit about how this health streak look like. What are the properties of these health streaks? So there's some messages here that may be useful for all of you here, depending on your career stage. First, we find is that health streak is rather ubiquitous. Out of all these domains we study, over 90% of people have a health streak. All right. A second we see is usually unique. Most people have just one. All right. And then we see that health streaks occur randomly within a career, within a sequence of work, that with equal probability, it could be your first work, last work, somewhere in the middle, and that reconciles the idea of random impact rule, namely if a health streak occurs randomly, and then your batch work, second batch work, third batch work are statistically more likely to occur within health streak, then that would explain why in the real patterns we observe these hits all appear randomly, right? And we also see that health streaks don't last forever. Usually they last about 4 to 5 years, and then appears to be unassociated with productivity change. In other words, we don't see you produce more than we would expect you otherwise. It's just what you produce during that period is better than everything else you've done in your career, all right? So the paper was published and it was actually quite a happy time, but when the paper was published, I remember there was something deeply unsatisfying about the paper. So I actually then, it was so unsatisfied, I actually wrote an op-ed to Wall Street Journal to talk about this. And the reason is, when the paper was published in 2018, but it's way back then, we really just reported a new phenomena that seems to occur in the data, right? So I had no idea why it happens. Like, what explains when the health streak starts. So to me, this is like unfinished story. So I wrote the op-ed. This is exactly quoting from what I wrote in that sort of, I think the central question now is to think about, is there any identifiable regularity underlying the beginning of health streaks? Because to me, that's a better question, because if we answer that question, then that will allow us to ask a range of new questions. For example, can we anticipate the start or the end of a health streak? Can we create an environment to facilitate the onset of health streak and to extend it when it emerges? For someone who has had a health streak, can we treat it as an indication of that person's potential and help that person realize that potential again, right? So part of my optimism of writing this piece was also, I thought, within a year or two, we'll find the answer, we'll have another paper, right? So what happened since then is one failure after another. So it quickly blew up in my face, which is in the year following this, we tested about 10 different hypotheses. Each of them are extremely plausible. And you may actually have your own guesses, but none of them worked. So I remember then I went to NIH, and at the time I was an advisor for the Office of Directors, where I was analyzing all their data. And then so I went to NIH to give a talk to all the program managers. Right? So it's a very big podium. And I remember I was sort of just presenting them about health streaks, but then I sort of expressed my frustration that we don't really know why it happens, right? And then, and for NIH, this is the concept that's very relevant, right? Because in science, for example, many of the decisions in science are based on a projection of future impact. Think about awarding a promotion and tenure, think about awarding of grants and awards, hiring, all about a projection of future impact. So what health streaks tell us is that actually the impact of a career is rather uneven. So that means if you ignore health streak and its singular nature, it may lead us to over or underestimate the future impact of a career, right? So after my talk, an NIH program manager came to me and I actually said, hey, Dashun, like, don't you see it? It's so obvious why health streak happens. And I was like, well, tell me. And then so he said, well, you said it's 4 to 5 years, right? You know, we funded them. It was our grants that funded their health streaks. And then the grants is gone and they're done. And I was like, well, you know, it doesn't explain the artists, but it does have an important virtue, which is a testable prediction, right? So then I went back home and got my students. I said, wow, let's actually get all the NIH awardees. And let's look at, here is the health streak. The grant actually just came right here, right? So now we have some data. So it turns out, once we look at the data, the NIH grant came exactly when the health streak is about to end. Does that make sense now? So when do you get a big NIH grant? Is after you do one Nature paper after another, and then in their terms, also enough preliminary work, and that's where you get the most money, right? So in this sense, you know, by funding proven scientists, it does protect NIH investment, right? But the question is then raises is, are we funding streaks or retirements in this case, right? So, but the broader question, I think this example illustrates is just, well, health streak is the intuitive concept, but how do you incorporate this in your calculus is actually much easier said than done, all right? So we actually now have some answers, so I can actually talk about this. So the epiphany of understanding this question happened right here in the museum, Van Gogh Museum in Amsterdam. All right. So I was visiting Amsterdam. I was walking around the Van Gogh Museum, and I remember it was exciting because I know Van Gogh was a data point in my sample. I know his health streak started in 1888 when he moved from from Paris to south of France. And so I was walking around the museum. You know, I'm art amateur, but you know, even when I walk around the museum and when these paintings are arranged in a chronological order, I actually feel like I can see some difference in the way that he paints before 1888 and after 1888. So that's where I actually pull out my phone and send my student a WeChat message right there. Just say, we have to look into these paintings instead of just analyzing the metadata, all right? So by the time I get back, my students then collect a whole range of new data sets, right? So the new data sets includes now we have over 2,000 artists. For these artists, we not only just have metadata about their work, but also know the images of these artworks that they produce, right? And then for the film directors, now we're looking at the plots of the films they direct, and as well as cast information to approximate sort of what this film is about. And then for scientists, it turns out to be the easiest because we already have the publications. We just look at the papers. So then this is where, you know, you realize, oh, so now I can walk around a Van Gogh Museum for a day, but 800,000 images is going to take a while, right? But this shouldn't be anything new to CMU students where, you know, this is where AI to the rescue, right? So this is where another example where if we had this data, say 10, 20 years ago, we wouldn't really know what to do with it, right? So in here, we actually did something very simple. So we just took a VGGNet, and then we fine-tuned it with a fully connected layer, and basically reclassify VGGNet to classify art style labels, right? So basically using the image recognition capability that recognizes shapes and objects, etc., and then readjust it with a fully connected layer for art style labels. And once we do that, then sort of this is broadly just convolution layer, max pooling layer. But once we do that, you'll see then in the, this is what the AI sees, is that if it's a lower level layer close to input, this will capture lower level features like line orientation or brush strokes. If I take a higher level layer, and this will capture higher level features, objects and shapes. So then if I combine these kind of features, feature space, and then I'll have like a high dimensional space to represent what this painting roughly looks like, right? So if I do that similarly to movies, you could think about I can do a word embedding for the plot, as well as a node embedding for the cast information, who plays the role with whom, and combining these two, then that will give me a high dimensional space to represent each movie. For scientists, we could also do a word embedding for papers, but in this case we did both. The second method is something to follow someone in the literature that says, actually, if you just look at what are the papers are cited in each paper, and then you construct this co-citation network, it will already tell you what the topic of each paper is. So we just follow that literature to figure out for an individual, what are the different topics that they publish for each paper, right? So now we build all this machinery for a year, we can finally test some hypotheses. The hypothesis here I wanted to test is something that's very foundational in the social science literature, is explore versus exploit. Right. So the basic idea, so this is mostly emerged from the Jim March view, school of thought, and mainly been applied to understanding the performance of firms. All right. So the basic idea here is that if you think about a top performance, and explore and exploit always come into play, because exploitation allows you to go deep in a certain area and build knowledge in a certain area and refine your knowledge and capabilities over time and foster a reputation related to that capability, right? So exploitation may be actually relevant for health streak, but we also know exploitation quickly leads to stagnation because it's a conservative strategy, right? So then by contrast, the exploration actually may be quite useful because exploration engages in experimentation towards to the area that you normally wouldn't go. So it increases your chance to stumble upon a great idea, right? So then exploration maybe actually it's a variance enhancing strategy, sort of more likely to generate a big hit, right? But it's riskier. So the question here is that, are career health streaks reflective of exploration or exploitation? Which one is it? So when we look at this, what we can do is just use our sample, line everybody up in terms of when does the health streak begin, and then look at the work that you produced before and after when health streak begins. And here we just measure a very simple is an entropy measure in terms of the different R styles topics that you pursue, right? So in this picture, we have three key messages here. So what do we find is that before a health streak, the entropy of the work is systematically larger than expected. So what it means is that it seems like individuals tend to diversify the topics they work on, and this is consistent with the exploration strategy. Once the health streak begins, the entropy of the work becomes systematically lower than expected. So this is consistent with exploitation strategy, where individuals all of a sudden become very focused on what they work on, right? So, and third message is that despite the differences across the three domains we study and the methodologies we use to study them, this idea of exploration and exploitation to be associated with health streak is more universal across all these domains we study. So we then look at, well, could it be just exploration itself was important, or exploitation during health streak without prior exploration is important? And we actually find neither cases. Neither cases explains health streak. They're actually negatively correlated with health streak. The only combination that's positively correlated with health streak is exploration followed by exploitation. All right. So then the plausible explanation on this, and this is correlation, though, and this is association, right? So it's nothing causal here. But a plausible explanation here is that exploration is this risky strategy that enhances your chance to stumble upon some great ideas. Try a whole bunch of things. Think about a capability building, right? Exploring, and then exploitation then allow you to go deep and focus on that area and really develop this further, right? So together, so this is a combo, and both ingredients seem necessary. So this positioning of exploration before exploitation serve to expand your creative possibilities, right? So that's good because it's a question that's been puzzled me for a long time, and finally we had. This is so far the only consistent factor that we know that predicts the emergence of health streak across all these domains, and hopefully people will discover more over time. But and then I got myself into the next question, because now we know explore and exploit is very important, right? So then I thought I want to start understand a little bit more about the first step. How do you explore, and how effectively can you explore? So this is a very simple question, but surprisingly, this is something actually we don't know much about, all right? So this is a new project we've been doing. Hopefully it will come out next year, where we wanted to look at adaptability of science and technology and how effectively researchers may adapt to new areas. So here, the basic idea here is that, we know that science and invention face an evolving array of questions, problems, and opportunities. And we also know that adaptability to threats and opportunities is essential to the performance and survival of organizations, economies, and societies at large. But very little is known about how successfully researchers actually adapt to shifting demands. And so in this paper, we study adaptability, and we're going to do this at different levels of evidence. First, we're going to do a general fact finding. General fact finding is just use large-scale data sets of the old papers and patterns we can find and try to see if there's a pattern that's robustly emerged, right? And second, building on that pattern, we're going to do 3 case studies. These 3 case studies are going to strengthen the causal interpretation of what we find. That will include first 2 natural experiments. And these natural experiments is where researchers were pushed to move. And we want to see if that replicates what we discover in general facts. And then after this 2 natural experiments, we're going to look at one high-scale case where researchers were pulled into high-demand areas. And in this case, we want to study COVID as a case study and to think about that, does the findings still replicate there as well? All right. So this is kind of a general roadmap for this project. So I'll dig a little bit deeper onto this. So the theoretical framework conceptually, and this goes back to explore and exploit, right? So is to think about how do people adapt. In this case, exploit is to keep doing what you do. Explore is enter new area. And so if you look at literature, you basically realize the literature will expect both. It's very ambiguous, right? Some will say the exploration may be actually very hard. So the basic idea here is that the world is becoming more and more complex. As a result, individuals are becoming narrower and narrower. So it's increasingly harder to traverse the knowledge terrain and bridge the gap. Right? So this is the narrowness of expertise point of view, mainly building on my colleague Ben Jones's work on burden of knowledge. But if you look at the creativity literature, it also suggests that exploration actually may be quite productive. For example, the creativity literature, people study novelty and tend to emphasize novel combinations may be especially fruitful. Also in Silicon Valley, there's this hypothesis that outsiders tend to offer some crucial advantage. Right? Those are the ones who are going to come in and disrupt the new industry, right? And also, if you look at the team science literature, you can also realize, okay, well, individually we're very narrow, but we can form teams and collaborate and help us extend reach. So maybe collaboration is a way for us to circumvent this, right? So then the question is it easy or hard? So we're going to look at all the papers, 45 million of them, and 3.7 million patents, and also the COVID-related work on 2020, right? So in this case, we devise a measure to quantify how much did you pivot, how much did you deviate from your prior work. So we aim, there are different kinds of measurements. We tried a whole bunch of them, rather robust, but this measure I like the most because it's very simple to explain and it's very easy to apply uniformly to everyone. All right. So this measure basically is to say, let's look at for an individual, let's look at all the prior works this individual published, and look at all the journals that these papers draw on, all right? So this is approximates the knowledge stock you usually take in. And then I have a vector to represent this kind of a knowledge stock, all right? So this is your usual knowledge stock. And then if you publish a new paper, I can look at all the references in this paper and see, does this vector look like this vector? If it looks like this vector, then it's a small pivot. Typical, same old, same old. But if this vector looks nothing like your previous vector, then this is a very large pivot, right? So it's very simple, just cosine similarity. So we look at this, all right, so we give you an example. Here's the distribution of this measure applied to all scientists and compared with COVID-19 work. So give you a sense of face validity in a sense. You see, normally in the pivot size, is actually a wide spread dispersion across the cases, between 0 and 1, right? But if you look at a COVID, it's a very clear red shift. Everybody's pivoting very far, right? It's because it's a new thing. So this is sort of just a sense of the measure. So now the question is, what happens when you shift from your existing area? The key results is really this one single plot. So here I'm looking at, as a function of pivot size, what is the impact? What you see is a monotonic decline. So what it means in plain English is that as you move further from your prior work, the work sucks, all right? And so this is what we then later start in the paper we call pivot penalty. It appears to be a strong penalty in terms of your impact. And then we look at, okay, what about over time? And what you see is that this curve is growing steeper over time. So this is like this penalty is getting worse and worse over time, right? So, but then you look at this intuitively, you think about, okay, so maybe there's some trade-offs. Maybe on average is bad, but boy, the best work is the one that you really try something new, right? So we're like, let's look at the tails. So if you look at the tails, what you see is that actually there is no reversal in the very upper tails. So what it means is that actually high pivot work, they do systematically worse across the impact distribution, right? So there appears to be no trade-off whatsoever. So it's just bad, right? And okay, so what is happening here? So let's think about some potential mechanisms to explain this and sort of start to unpack this a little bit more. So what might drive this? And there's a whole range of literature can inform us this, all right? I'll give you some ideas, and now I'll tell you some ideas on how we attack this. One is to think about reputation effect, right? So the idea here is that, researchers may be particularly well known in some fields, and then when they move to a new field, no one knows them. So therefore, impact is lower, right? So this is basically thinking about the Matthew effect literature or typecasting literature in sociology. Or you can think about maybe there's something about the work itself, it's the substance of the work. It's because researchers may be really less skilled or expert in areas that's new to that person, right? So it's not much of a novelty. It's new to that person, but it's not new to the world, right? So this, we think about this as a creativity literature or human capital literature in economics. Or it could be a resource story. For example, high pivot may come with less grant funding, fewer collaborators, a less creative part of a life cycle. So this is more like a science of science literature, right? So I'll give you some tests on this, and I'll give you some ideas on the high level, how we attack this. So we tested a whole bunch of hypotheses. In terms of reputation considerations, this is something we spent a lot of time to think through. There are two empirical ideas we wanted to pursue on this. First empirical idea is to say, why don't we study only the publications by researchers before a common audience, right? So the basic idea here is that what happens when the person is publishing multiple papers with different pivot size, but in the same field, journal, and year, right? So you're putting in the same kind of a journal on common audience, but the variation is a pivot size. So what happened there, and what you see is that still happens, right? So then the second idea to continue to test the reputation consideration is to think about, okay, so what if we consider recognition? Well, we also know citation is a frowned upon measure, and so science citation, there are many issues. So what if we look at a recognition by people outside the immediate community? All right. So here we use two measures. One is for scientific papers, we want to look at, how much is this paper cited by patents? So the hope here is that you may be particularly well known in your scientific area, but the inventors who build on your work don't know you as much anyway. So no matter where you move, all right. So we want to see how does the marketplace value this work, all right? And the second measure we use is this called a KPSS measure. KPSS measure is to look at when the patent is being issued, how much does the market value moves in that firm. So this is marketplace reaction to issues of patent. So this is sort of, you look at this. What do you see? Again, you may be, as an inventor, you may be particularly famous in certain sphere, but the market shouldn't know really who you are. So I was trying to see if this is sort of the same as people outside of your immediate community, and we're seeing the same patterns over as well. So if we go, so it's not just reputation, right? So then let's look at the idea generation framework. So in the creativity literature, you think about new work as a combination of existing ideas. Here we're drawing on Oz et al. Paper, which unveils that home run ideas tend to have two features. One is building on injecting atypical knowledge, tail novelty, and then high median conventionality. In other words, you're really injecting cutting edge knowledge, some atypical combination to a well-established body of work. So this is sort of, I often call that paper as 90-10 rule, or 90% of conventionality and 10% of novelty. Usually that's what predicts the highest impact work. So we took that framework and applied it to our sample and think about, as we increase the pivot size, what happens to your novelty? What happens to your conventionality? Very interestingly, what you see is that as your pivot away from your work, actually the novelty increases. So what this means is that if as you pivot further, you're not only creating knowledge that's new to you, but you're also creating knowledge that's new to the world. So the novelty did not suffer. But what did suffer is conventionality. It sounds to us is that as you increase your pivot size, the conventionality of the work, how much you can build on the conventional knowledge sharply declines, all right? So then what that then takes out is then we know that highest impact work needs to have both high degree of conventionality and the novelty. But it looks like the high pivot work is missing half of the picture, all right? So we look at some research shops, and in this case, what time should I stop?
We have until 1:30-ish.
1:30-ish, okay. Okay.
Yeah, I would within 10 minutes and then Q&A.
Oh, okay.
That's what we usually do.
10 minutes,
We don't
good.
usually go
10 minutes is
all the
good. Okay, I'll race through this. So look at some push events. So to try to improve the causal interpretation of this. So the basic idea here is we want to look for events that's exogenous and researchers were provoked to move. So in this case, we look at two settings. One is retraction, the other one is reproducibility. So here, there are people study these settings, but the difference here we study is that we don't look at people who retracted or people whose work didn't reproduce. What we look for is the people who were citing this work, all right? So that's the difference. So sort of when you cite this work and you are building on this work and all of a sudden you see these giants all of a sudden became shady, then that may provoke you to pivot. And then we want to see if that provoke to pivot would predict, impact difference as well. All right, so that's kind of the causal strategy here. But what we see is a very consistent story, is actually of much larger magnitude. It turns out if you are forced to move, it really sucks. And so then you realize, oh, this actually makes a lot of sense, because what we observed in the large scale data sets is that, researchers, they themselves chose to move amidst all kinds of calculus of trade-offs and returns, but that didn't work. So now if you're pushed to move, it really not gonna go very well. So then that raises the question of, okay, so what happens with COVID? Because in COVID, a lot of people did COVID research and it seems to work out great for them, right? So this is sort of, you pull into a high demand area, what happens? So we replicate this for COVID. So what do you see? This is right curve is the COVID curve, right? So what you see is on average is an uplift. So that's consistent with the high demand nature of this area. And so it's an impact premium when there's high demand. But you see the pivot penalty now is so steep that if you actually traverse over medium distance to actually engage with COVID, you may be actually better off not doing it. All right. So what it means is sort of you realize, oh, the people who work out great for them when they do COVID are the ones who are already developing mRNA vaccines, already doing epidemic modeling, already gonna do a field experiment on vaccines, right? So these are the people that work out very well for them. So then this actually creates a new issue for us to think about, which means what happens is that it appears to be pivoting to a new area is both hard and costly. So because as a society, we don't know where new threats and opportunities may emerge. And when that emerges, we may actually have a very limited opportunity to shift resources effectively to meet new demands. Right? So then what this has as the implications for us to think about science policy and how do we think about society as a whole to be better prepared and respond to the new crisis, right, in the scientific community. So this is something we've been thinking. All right, so 5 minutes, I'll talk about the new stuff what we want to now embark on. It's called Tech Bridge. Tech Bridge, you see this map, actually CMU is not on the map. Don't you worry, tomorrow I'm meeting with your VPRs and try to fix this. So this is something that we started to do. And let me tell you sort of basic idea of this. So we started at the Northwestern and we wanted to think about, okay, now we learned all these insights. How do we use this to help institutions and especially accelerate progress? And so this started with Northwestern leadership came to me and said, hey, you study all this stuff and why don't you study us? So then we started collecting the data that Northwestern has, which is also the data every university has. So what does the university have? So the data they have will be the tech transfer offices in terms of inventions, licensing and startups, sponsored research in terms of grant applications, funded and unfunded grant applications, approximates all the ideas that faculty members generate, alumni data, scholar data in terms of papers and citations, HR data, basic characteristics, faculty awards, etc. So we integrate it. It turns out when your university president wants you to do this, it's very easy to get everybody to get your data. Once we have this, we can link with everything we've been playing with in my lab in terms of all the papers and patents and citations, drugs, clinical trials, policy documents, etc., right? So then then we can not only measure things within the university, but we can also benchmark worldwide. Right? Let me give you an example. So it turns out if you look at this data for the first time, then there's a lot of insights that you start to discover. Let me give you an example of this Kathy, faculty member Kathy. Kathy is a female senior faculty member in our medical school, highly productive, has like hundreds of millions of grants, hundreds of papers, etc. Right? Very well known. When we discovered her, we realized she's never knocked on the door of our tech transfer office, never patented anything. So what that means is that if you analyze patent data, she doesn't exist, right? We can find her because we have the whole roster of university. So we had the zeros, in other words. So when we look at her case, what we see is that actually all her papers, they're being cited left and right by other patents. Right? So this is the new data linkage we now have. When the paper is cited by patents, we know that. So we can see, okay, what kind of patents is this? And we say, oh, it's not other universities. This is a lot of other companies. And we say, well, which companies actually cite her papers? And we say, oh, there's this German immunotherapy startup company where 10 of their patents are based on Kathy's work alone. So our collaborator, who is the head of our tech transfer office, who now stepped down to help me with this initiative, when she saw this, she was like, oh, I know Kathy. Let me go get a coffee with her. So the next day, she had a coffee with Kathy. And I was like, Kathy, so do you know about this company? And then she's like, no, I had no idea. I did a sabbatical in Germany and I had no idea who they are. And then she's like, well, Kathy, do you know your papers are having this kind of market impact? She said, no, I had no idea. I imagine it's the same. Do you know your papers being cited by some patents? You probably don't. And then she's like, Kathy, why don't you patent with us or do something around the innovation? And then she's like, I'm very busy, all these ROI grants, committee members, etc. And so the typical excuses. What's really interesting is that within a week of that coffee chat, Kathy filed her first patent with Northwestern. So when I heard about this, I was like, wow, I have so many questions. How many categories are out there? It turns out at Northwestern alone, within tenure-line faculty member, we have about 100 faculty members like this. And then another university president heard what I'm doing. He's like, I don't know what it is. I want you to do exactly the same thing for us. So then we went to their university, which is another R1 university, and then we found another 100. All right. And then the third university heard, oh, I want the same analysis done here. And then we find another 100. So this is where I'll give you an example why this is simple to illustrate why there appears to be a vast amount of untapped innovation potential within the university setting. Here's the example. If I just look at a male-female faculty member in terms of how much they patent, you see a very big gap, right? So this gap is so big that you don't even need statistical tests. But if you look at, okay, how much of their papers are being cited by patents, you see actually they're basically indistinguishable from each other, all right? So what this means is that this is not only just a DEI issue, but also research shows that female faculty members have unique insights for women's health. So if inequity in who invents will also lead to inequities in who benefits from this kind of inventions, all right? Or another way, if you look at it, just a tenured faculty member versus tenure-track faculty member, you see another big gap, right? So here you see the differences is rooted in other factors, especially in terms of promotion incentives. But we all know it's not like once you get tenure, all of a sudden you're more innovative. No, it's really sort of some structural factor here. But the point being, sort of, you can see there are vast amount of untapped innovation potential that can now be systematically identified and pinpointed with both data and AI tools we've been developing. All right, so this is sort of a range of tools we now developed. I recently wrote a Nature piece to illustrate what we're doing on this, so feel free to read and have a better, it's a very short piece, it's an easy read. So the idea here is, how can a university locate key ideas, personnel, and partners to maximize its impact and accelerate progress? So here we want to develop a whole range of data tools to use high-scale data and novel tools using AI to survey the entire landscape of research activity, and both at the university and worldwide to find untapped potential. And here the key is to think about human-machine partnership. And these tools are meant to provide leads and attention to specific decision makers who can then evaluate this and decide how to pursue, right? So in other words, these AIs are not to come to take anyone's job. It's really people who use our AI may take the job of people who don't. So this is where sort of we started at Northwestern and we go to the next university and more university coming to me. And I was like, well, this is quickly becoming impossible to handle. So I came up with this idea. I said, well, you know what? I'm going to go to NSF, ask for $20 million. And then if they give me the money, I'll do this for everybody for free. And initially we have a sign up of 22 universities in the US and UK. And by now, so fast forward, then we got the money. So they give we got the 20 million for the next 5 years, and then the words are out, and some university quickly realize, oh, why am I not on the map? So now we're quickly expanding to over 30 universities. But if we actually succeed to onboard about 20 universities, we'll be account about roughly 20% of the entire US R&D spending, sort of in aggregate this kind of data, right? So, all right, so concluding. Hopefully what I went through a whole range of projects is meant to convey that there seems to be enormous opportunities to better understand and improve science and innovation. And the science of science as a field is producing new discoveries that can reshape and accelerate innovation systems worldwide. Policy-wise, there are enormous potential to do more and do better, and the stakes are extremely high. So the way to think about this is that people say science is a fundamental engine for human progress, but I like to think about science as a little engine that could. So if we can make R&D even 5% more efficient, then the returns to society will be enormous in terms of living longer, healthier, happier lives. And if we apply all this to a research institution or a nation, the lessons make really advance the R&D success and accelerate human progress, all right? So I'm gonna conclude there. There's some other resources. People often ask me, oh, how do I get into this? And how do I get the state-of-art data? Don't you worry. Now we publish SciSciNet, which is an open, cleaned up data sets ready to use for research purposes. Go get a copy and start coding and start cracking. And because in part of we built this database is because I got like an email every other week to ask me, hey, can I get some data? And now like, you know what, now I publish this data lake, that email just dropped to 0. No one's asked me anymore. So that's fantastic. And then I start to get a new emails, which is, hey, the data lake is too big. Can you help me compute from the data and do the research? And so I can publish. And I was like, this is kind of a new kind of email. And so that's where we realized we're building what's called a SciSci GPT. All right. So now this is a wrapper around and customized around Claude 3.5 as well as GPT-4, that GPT that understands the literature, understands the data of cyanide, understands the typical methodologies, and has a self-evaluation so that any email that I get, the question they ask, they can just get there, and then the SciSci GPT is an agentic feature to then figure out how to respond to this and code things and SQL queries, get the data, analyze it, present it, etc. Hopefully we'll show that quickly. It'll be able to publish that soon. And we also recently wrote a review paper to illustrate the diverse kind of empirical methods that we use in the field. So this is sort of different kinds of review paper in that it wasn't oriented around topics, but around data measurements and empirical methods. The hope is to help newcomers to the field to enter the field, right? So, and obviously there's also the book that could be a good starting point. What I want to emphasize is it's freely available, so don't waste your money. Although it's getting colder, so it's good to have the physical copy to feed your fireplace. All right, so super grateful for a whole range of funders that support our work. And we are hiring, so go to our website. We're hiring big time, so please reach out. And if you want to be part of it, I would love to collaborate. So yeah, thank you very much.
Any questions, comments?
Going back to the example of pivots, you talked about the impact of the first paper after a pivot. Have you looked at what I would imagine to be a common pattern, which is low pivot, low pivot, low pivot, high pivot, low pivot, low pivot, low pivot to continue working in the new field?
Yeah.
Have you looked at the impact of the successor work in the new field?
Great question. So we have looked at it, but it's inconclusive. So this is something we mentioned. We wanted to think about future work. Inconclusive in the following sense. What you said, I think, is a very plausible scenario, and it does mean what happens when we look at the data is that low pivot, and high pivot. But if you continue that area, then that's basically the hill climbing back up that pivot penalty curve, right? Because you already did
get better at it, you get better now.
Right, but then you are also, if you just look at a measurement, if you continue this area, then by definition, you're lower pivot because you already pivoted, right? Because that become part of your existing body of work. So you see that pattern. But the reason I say it's inconclusive is that there's a lot of endogeneity here, because if you stick to it, it says a lot about like that kind of work and how it clicked with you. So we don't have anything further than that, right? So always to say this pattern could also be, there's a lot of endogeneity in terms of whether you pivot and didn't work, and then whether you continue to do that work is very much revealing, and there's a whole range of confounding factors that explain that subsequent behavior. That's why it's inconclusive. So I think I'm very curious about that question. If you have any further thoughts, let me know, because that's something that it was super sharp question, because that's exactly the hole here. We don't really know.
So you're using Google Scholar for science, but science goes back way before Google Scholar. And in fact, Google Scholar's coverage, at least in computer science, gets shaky as you go farther back. and the citation patterns have changed a lot. So have you normalized in some way the course of a scientific career? 500 years ago, life expectancy was much lower.
Yeah.
40 years ago, there were mandatory retirement ages. Have you normalized for where in the course of a scientific career the work is being done rather than using age as an approximation?
So yeah, great question. So here, just clarification. So we use all kinds of database, combine them. Google Scholar in initial papers we use primarily relying on their Google Scholar profile as a name disambiguation method, right? So that
Google Scholar is a dumpster fire, aside from that.
yes, but what we then do, we use that as a collection of papers for each name. But then what we do is we connect to the curated databases, Web of Science, Microsoft Academic Graph, and Dimensions in particular recently has been really, really helpful. So that's kind of, that's the detail I didn't get to explain. So we're leveraging Google Scholar profile as a disambiguation tool, but the citation publication patterns, we use other databases to cross-validate. To the question of temporal trends, yes, there are temporal trends. For example, if you look at the peak of your highest impact work, that peak shifts in terms of time or discipline, right? Some mathematicians is different from neuroscience, so you can see that shift. But what's really interesting is, but if you look at a random impact rule, they all very robust. So we report that in the supplementary material, is that a different era, they may peak in different times, or different fields has a different kind of peak. But the random impact rule all seems to actually rather robust. And the third one I want to clarify is, we didn't look at age. So what we look at is the sequence of work you produce. So your age 0 is the first paper. Your age the end is your last paper. So, and that's just out of limitation of data because we don't have age for everybody, but that turns out to be helpful for us. For example, my favorite example is John Fan, who, anybody know John Fan, who John Fan is? So he showed up in my slides and didn't get into it. So John Fan was a Yale faculty member, and he then hit mandatory retirement age. And then Yale was super happy because after all, he's been pottering around, not doing much. So then they forced him to retire. But when he was about to retire, he's trying to convince Yale that he has a new idea, and this idea is gonna be great. And then Yale just obviously had no patience, so kick him out. And then he went to Virginia Commonwealth University. Anybody know Virginia Commonwealth University? Good. So, and that's the only university allow him to build a lab. So then he continued, and that's, if you look at his career pattern, that's where his hot streak happens. One paper after another, where he invented what's called electron spray ionization, which becomes a key technique to measure the mass of large molecules, which then spur a whole range of new therapeutics and cancer therapies. And that then won him Nobel Prize in chemistry when he was 92 years old. So very good example in thinking about sort of, instead of looking at age, and when we look at papers, we actually sometimes have a broader coverage in this case. Yeah.
Can you talk about, I'm curious about when people make pivot in their career, is it because when they are in, I would imagine that as a PhD student, you would try to gain some expertise in one field, whereas if you become a tenured faculty, you have more appetite for risk and therefore can afford to pivot. So have you tried to explore those trends and see where people are more successful when they pivot?
Yeah, great question. We tried a whole bunch of things, different papers too. We actually just posted a paper, I think this month, but I guess November, to understand tenure. What happens before after tenure. So this is a new data set we had where we finally had a when do everybody get tenure across the US. So then we can line everybody up and finally in terms of this is when you get tenure, what happens before after tenure. So now, so this is a paper now on archive on that. What you ask is a very hard question in that, I don't know, have you guys read Range, that book by David Epstein? It's a really good book. It's follow on Malcolm Gladwell's book of Outlier. The hard part of that is endogeneity. People who can traverse very wide terrains are also great people. So that is a very hard question, right? Because I think what you want to say is condition on you're the same person. Would it be better for you to go very broad or narrow, right? That's a very hard question to answer. I don't think we have real clear answers on that yet. But there's a lot of plausible ways to think about this, to think about early career capability building, a larger exploration could be very helpful, and we do have evidence for that. But I just want to caveat, but there's another side of a story where if people can explore very broadly, may by itself be indicative of some characteristics that predicts their future success that is difficult to observe, right? So that, I think that's kind of the problem here. But there's a lot of evidence in support. If you explore a lot, in the long run, it works better for you. And but I think if you think about, so my thinking is a lot about explore and exploit. I think this is something I want to think more. And it's also quite surprising, actually, given how much we know exploration and exploitation. Jim March was probably cited for, 50,000 times. But it turns out no one has ever said this temporal separation of exploration followed by exploitation. I would like to know if you have a literature, because I thought this is people have understood this for many times, but then some people really, the management scholar really deep into literature, were like, you know what, actually that's new. I never heard about anyone says exploration followed by exploitation, because it's always about trade-offs. So the literature, thinking about Michael Tashman from HBS, is about ambidexterity. So how do you think explore, exploit? Do both at the same time. And because a lot of these are in the firm setting where you can do both. But I think for an individual setting, there's opportunity cost. It's difficult to do both. So I think a lot about the separation. Then you have an exploration phase, which is a capability building, and then you have exploitation, which is sort of developing and sort of really to go deep. And so, but if you think about that in terms of career stage, it's also interesting because what I hear you're saying is that if you're tenure track, you should be exploiting. And if you're tenured, you should be exploring. So you see, it's the opposite of explore than exploit. So I think if you think about science, it's a lot like that, in that it's actually the opposite of what we are discovering, in the sense that the current structure that's set up appears to be in tension with this kind of dynamics, which is something that I want to explore more, but it's something that I've been thinking, but right, in that respect. Yeah.
Just I wanted to make sure I was understanding the pivot score a little bit. Maybe my question is posed. It's sort of like a distance measure, right? Between work you've done based off the things that you cite in your current paper and the things you cite in your next paper. But there's also distances between those topics, right? So if you go from biology to physics, or very different fields of science versus subtopics in the same fields that have different literature behind them, but maybe there's more shared knowledge, shared background. Did you capture different types of pivots like that?
No. We could, but no, we haven't done it. We thought about it, but it's actually harder. We actually have the reason it's hard is that we actually have a whole project just to try to capture the distance between fields. But by itself that's a new area by itself. So that's where we haven't really done a good job on that regard. Yeah.
Because there are definitely examples of scientists who have done very well by picking very different things within the same field.
But so we're hoping that will be captured by the journals you publish. So that's kind of the hope here, right? Is that, you know, there are a lot of people in the literature that seem to suggest that journals is a proxy of certain field, however narrow and broad it's defined. So that's what I was hoping with this measure. But journals are also different between different journals. And how do you calculate a distance? My intuition is there's got to be some co-citation measure that can help you understand the similarity between journals. And then maybe incorporate that in terms of weighted cosine similarity measure to think about a weighted average of the pivot size. Now that I talked about this, I actually realized we may have done some analysis, but I'm not sure it's in the paper. Yeah. Yeah.
So when you put up the figures showing the the success of explore then exploit, you also had a figure, right? Also in that figure was exploit then explore, and was very negatively.
Yeah.
I wonder, is that mostly pivoting in some ways, that somebody is sort of focused, so they're exploiting first, in some other field, and then the explore or is the explore measure conditional on in a field, or is it sort of, would it be capturing that dynamic where you would be, you focused on something and now you are seen to be exploring, but it's a pivot.
Right. Wow, interesting. So just clarification. So when we say explore, exploit, or exploit, explore, we impose a period. So it's a period where you think you're more exploratory, try different things.
Right.
And so it's not one work. Pivoting is more one work. And I see. So this is exploration would mean, so in this period, you're unusually trying different things, right? So in that sense, it's similar but not the same with pivoting. Another pattern, so maybe it's useful to talk about this. So another pattern we spent a lot of time studying is to think about, is this like an oil drilling process where you're exploring and then you find it and then you double down, right? So then we really get into it and we look at it, and then so what we can do then is look at this thing that you exploited, that explained hot streak, where did it show up during the exploration? And what you see is that it's actually less likely to be the last one you explored. And it's also less likely to be the most popular one during the time, okay? And this is in science, where we have more data, it's easier to test. So then what I suggest that is not an oil drilling process. What is more like, I don't know if it works, but what it's more like is like a buffet process, where you go to the buffet and you sample a whole bunch of things, and then you eat it. And then you go to the next one, you'll be more focused, but you're gonna focus on the ones that really worked for you instead of the most popular dish in the first trip. So I don't know if that works, but in my mind, it's more like eating buffet than oil drilling.
That's a lot less random.
Uh-huh.
I mean, right, because it's like oil drilling is just sort of
Right.
keep trying things and then the last.
But they would have same explore exploit type of pattern, and then they will have different kind of policy implications, right? But it seems like it's not always drilling, so this is something that's maybe interesting. Yeah.
This is a question about cheating fields. Herb Simon used to advise young scientists to understand what your particular comparative advantage is, what kind of analysis you're particularly good at. Are you an empirical person? Are you a theoretical person? And to look for research problems that exploit that skill. It seems to me that this is somewhat orthogonal to what you've been studying, and that there's a possibility of field switching and diversity in which you deliberately switch to a field in which your particular talent can be brought to bear on problems. Is this something that falls within the domain of things you can study, or is there just not data? It's sort of like, does this research paradigm carry over to another field? And does someone stay within that paradigm as they switch fields, or do they also switch paradigms?
Great question. So My sense is the Herb Simon's advice. I should have mentioned it, given that I'm in CMU. So my sense of his advice is more targeted with early career researcher, and this is something we want to try to do more these days. Because a part of this, I think a big limitation of our current work on this is that we've been focused on whole careers. So what that means is that the sample is people who have had a long enough career for us to study, right? Well, this is a sample that's of interest for scientific community anyway, but it does introduce a very strong selection effect, right? But it's selection, but it's a very big improvement over the state of art, just let's be clear, but it's still now it's a selection. The question is, can we incorporate the attrition that's really a very strong force that's happening and to study earlier careers? And especially if you want Herb Simon, I think the challenge is you especially want to get some data before the first publication as well, right? And because when he said you want to sort of find your competitive area and get into an area, that's almost like the first couple papers. You dabble a little bit and then you want to find one that really have your competitive advantage. And if you want, and it's, I think it's very much very reasonable in thinking he's right. And I think it's consistent with basically Michael Porter type of view in terms of competitive strategy of nations and how should you develop your competitive strategy. But it's very hard to test individual careers. And in part there's a lot of attrition. It's very hard to detect data early on. And the attrition is very difficult to trace. Even for the tenure track faculty, we're hoping maybe when we get a roster of all these universities, maybe that'll give us a more precise record of employment record, who is here, who is not here. So all this will be difficult, hopefully it will be easier. But yeah, we don't really have good evidence on an extremely early career, or say something there. Yeah. Good? Great.
Thank you so much.
Yeah.